All right, let's shade the region bounded between the graph of f of x equals 4 and the x-axis, so between this graph and the x-axis on the interval from 2 to 7, which I think is pretty straightforward. We're going to go from 2 to 7. There we go. That's what we're dealing with. And we are going to find that area. Great. Well, the area is 20 because I think we can find the area of a rectangle very easily. However, we want to write the definite integral represented by the scenario. We have done this. We'll continue to use blue just for fun. From 2 to 7, f of x dx. Why not t? Well, because we're not dealing with multiple variables all combined together. This is just against the x-axis. That's what we're really doing, okay? And we want to find the area of the shaded region. Again, we know the answer is 20, but we're going to talk about it in a slightly different context here. So here's what's really going to happen. I am going to find the area, and this is going to seem unnecessary, but it's going to kind of drive the point home what we're doing here. I'm going to find the area from 0 to 7, and then I'm going to subtract away the area from 0 to 2, and it will give me that. And I know you're like, that is so unnecessary. I hear you, I hear you, I hear you. Trust me on this. This is going to make a little more sense. First of all, let's change that f of x to be just 4, because that is the function itself. Okay? So let's just pretend, for example, that we were really struggling to find this area and we wanted to overcomplicate things. Then what we could do is find the area of, again, I said it a minute ago, this rectangle from 0 to 7. So let's suppose you're having a hard time counting to 5, but somehow you can count to 7 instead. That makes no sense. But you would basically have a height of 4 and a width of 7. You can do 7 times 4 or 4 times 7. I'm going to do 4 times 7. It's slightly strategic. So that would be this whole rectangle right here. Oh my goodness, I really want to know this. I've counted too much. Let's take away this part. Let's subtract that. So we're going to subtract 4 times 2. So we're going to subtract 4 times 2, and that's going to give me 28 minus 8, which gives me 20, and nobody is surprised at that. And you're like, what was all that for? Okay, let me tell you. Let me tell you what all that was for. We just did the fundamental theorem of calculus, the evaluation portion. And again, I'm not always going to call it the evaluation way of doing it. I'm just going to call it the fundamental theorem of calculus. It's a habit of mine, and it applies. So we are going to come back up here and tinker with this a little bit. So thinking of this in terms of an antiderivative. Whoa, what antiderivative? All this stuff confused me, Mr. Reader. No, don't panic, don't panic, don't panic. Okay, the derivative of what will give me 4? So just think, like, okay, what function would I have? If I took the derivative, I'd get 4. Well, 4x, that's what it would be. Okay, well, it's 4x. Now, there's more to write here, so don't be like, well, that makes no sense, and then 4x equals, no, hold up, hold that thought. I'm going to evaluate that 4x at 2 different values. Notice the little vertical line that just demonstrates, hey, I'm going to do something with this and evaluate it at certain places. And those certain places are 2 and 7. So I'm going to plug in a 7. I'm going to plug in a 2, and I got my answer. Now, I know you're thinking, well, it's a straight line. It's really easy. Okay, that's fantastic. Not all of them are going to be straight lines. Some of them are curves, and we can't use a geometric formula to do it. So that's why we use the fundamental theorem of calculus, where we will find an antiderivative, plug those numbers in, and calculate the exact area every time. So here's what's really happening. We have approximated area using lots of little rectangles when things were kind of funky to look at. We have done all kinds of things with rectangles and trapezoids and the summation of those things. And then we've also had situations where it was a rectangle or a trapezoid, and we can figure out those exact areas. But what if we have some curve like this? If as long as we have the equation, we can figure out the exact area using the fundamental theorem of calculus. My voice inflection may not reflect it, but this is super exciting. Okay, slide up and do the next one. Shade the region bounded between the graph of f of x equals 2x plus 1, there it is, and the x-axis on the interval from 4 to 8. Write the definite integral. Okay, well, let's just start by shading. So from 4 to 8. If you're anything like me, you're thinking, well, that's just a trapezoid. I hear you. We're not going to do it based on a trapezoid. We're going to find the area. It's a nice integral symbol I just wrote. Why, thank you. From 4 to 8 of 2x plus 1 dx. Okay? Final answer is going to be the area of this trapezoid, but I'm going to find an antiderivative. Antiderivative? What in the world is that? Okay, antiderivative, and there's a lesson devoted to this later. In the meantime, we'll just work with the idea we have. The antiderivative is basically like the derivative of what will give me 2x. X squared. If that doesn't go through your head, it will soon. Don't worry. The derivative of what gives me 1. That would just be x. And then we'd go from 4 to 8. Okay? So based on what we see here on the fundamental theorem of calculus, that had a very awkward beginning, but a very practical application and kind of straightforward, I need the antiderivative, because capital F is the antiderivative, and then we will plug in an 8, plug in a 4, subtract them. So let's plug in an 8. There's that. We're going to plug in a 4, and then we're going to subtract them. So 64 plus 8, 72. 16 plus 4 is 20. Final answer is 52. If, and I'm not going to, but if we found that exact same area using a trapezoid, we'd get 52.